Greetings, Internet users. Thousands of planets have been discovered around stars other than the Sun, many of which have the potential to host some form of life. We often hear about new planets being announced, some of which are potentially habitable or have the possibility of liquid water. However, it's important to note that a planet being potentially habitable does not mean it harbors life. It simply means it has the potential to support some form of life. Nevertheless, I'm sure many of you are unaware of the parameters astronomers use to determine if a planet can be habitable or not. Today, we will solve this mystery and explore the characteristics a planet must have to support life as we know it. Let's start with simple life forms like bacteria, progress to complex life such as plants and animals, and even consider intelligent life and technological civilizations. Specifically, a planet needs to be located in the Goldilocks zone of its star for water to remain in a liquid state long enough for life to develop. The Goldilocks zone, also known as the habitable zone, refers to a region where the temperature is neither too cold nor too hot for water to stay liquid, a range between 0 degrees and 100 degrees Celsius. However, that alone is not sufficient. The planet must also have sufficient mass, atmosphere, and gravity to maintain liquid water. Many might wonder why water is necessary and if there could be other forms of life without it. Water is a fundamental substance for the development of complex molecules, and it has been demonstrated to be quite abundant in the universe. Life needs to be based on reactive elements that can combine and form complex structures like DNA and amino acids. The best elements for this purpose are carbon, hydrogen, oxygen, and nitrogen. Water serves as the ideal solvent for these types of chemical reactions. Here on Earth, our chemistry is based on carbon because it can form complex molecular chains. Although it is possible to imagine other chemistries based on silicon or sulfur, that does not exclude the presence of water. Water will always be necessary for the development of living organisms. Therefore, if we detect a planet in the habitable zone or Goldilocks zone and it is rocky in nature, astronomers consider it potentially habitable. However, this doesn't mean it actually is habitable because we lack a lot of data about its orbit, composition, and especially its atmospheric parameters that are currently impossible to determine for exoplanets. We have hundreds of potentially habitable exoplanets to scan in the future, and the list may narrow down as we analyze their atmospheres. For unicellular life, water is an abundant element, and many planets should contain it in liquid form. However, it's not that simple. First, we need a stable star that allows enough time for a planet to form and become filled with oceans. Life forms through trial and error to create complex molecules. Some stars have short lifespans and emit too much radiation. These correspond to massive stars, which are the least common in the galaxy. Here we have the spectral range of stars, which corresponds to the scientific color emitted in the spectrum, not their actual color. O, B, and A-type stars are bluish and much hotter than the Sun. In the best cases, they can live a few dozen million years, and some don't even reach a million years. Additionally, they emit excessive radiation. However, A-type stars could potentially host some form of extremophile life for a few million years. What we do know is that the ideal range of stars for the formation of habitable planets should be F, G, K, and M-type stars. The Sun, as we can see, is a G-type star and is in the middle of the table. That's why astronomers always search for planets around this type of star. They can even exist in systems with 2 or more stars, as long as there is orbital stability with very low eccentricity, a circular orbit as close as possible to prevent abrupt temperature changes. So, let's consider the ideal conditions. Let's imagine a star that lives for several billion years. Let's assume it's a population 1 star with high metallicity, capable of forming planets. We know that the formation of a planet takes several dozen million years. Here we have a planet in the habitable zone of the star, but that's not enough, it also needs an atmosphere and water. The clearest example is our moon, which is in the habitable zone but lacks a significant atmosphere and liquid water. Let's increase the planet's mass by adding an iron core so that it can support an atmosphere through chemical processes in the interior and impacts from cosmic bodies. This process creates oceans. Microscopic beings can withstand a temperature range between 20 degrees below zero and 121 degrees Celsius, allowing them to colonize various environments. The ideal size for a planet to support some form of life should be larger than Mars and bigger than Earth. With that, you ensure a dense atmosphere with sufficient atmospheric pressure to maintain water in a liquid state. Then, we must wait for complex molecules to form in the oceans, and for that, a significant amount of time must pass. However, even if all the conditions are met, it is highly likely that life may never appear. Additionally, the star must be fairly stable, meaning it should not have significant variations in its brightness. This corresponds to stars in the main sequence phase, where they remain stable for longer periods. Life requires time and tranquility. As we can see, the formation of microorganisms is not so easy. However, the number of worlds is so vast that microbial and extremophile life can emerge in many different environments. As long as there is a liquid water ocean, life may even exist on moons of gas giants far from the habitable zone because the gas giant itself causes tidal heating on the moon, maintaining active chemical processes in its interior and liquid water. Simple life can also arise on a planet with a strong greenhouse effect that raises its temperature, even if it's in the cold zone of its star. Hypothetical forms of simple life in gas giant clouds have also been considered. Single-celled life can thrive in various environments, but under certain conditions. Summarizing, for simple life, we need A, F, G, K, and M-type stars of population 1, a habitable zone or satellites of a gas giant, atmosphere, and liquid water. How many celestial bodies do you think our solar system has that meet the conditions for unicellular life? Very few. However, Mars is on the boundary, outside the habitable zone, but on the edge. Its tenuous atmosphere doesn't allow for liquid water, but sporadic occurrences of seasonal brines are possible. As you can see, being on the boundary makes it a worthy candidate for study. However, studying life outside our solar system is more complicated. How would astronomers know if there is life on an exoplanet? Unfortunately, at this moment, we don't have the capability to detect the majority of atmospheres. However, if methane or oxygen, along with other important gases, were detected, the possibilities of life would be enormous. This is because some living organisms release certain gases in their metabolic processes. The next generation of telescopes, such as the James Webb, will be able to analyze complex molecules from other worlds. Complex multicellular life, including plants and animals, becomes more challenging. Environmental requirements increase for the evolution of multicellular life. It's not enough to have hundreds of millions of years. Billions of years are needed. A protective atmosphere with a magnetic field, ozone, water, and a planetary shield to prevent significant impacts are necessary. Only F, G, K-type stars, and possibly some M-type stars can provide these conditions. Then, we must wait for complex molecules to form in the oceans, and for that, a significant amount of time is required. The presence of an iron core is important as it aids in the formation of a magnetic field and ozone, ensuring that most of the radiation is stopped by the atmosphere. Preferred gas types are primarily considered to be oxygen breathers, although other hypothetical biochemistries could exist that utilize different gases for their development, such as hydrogen breathers in ammonia atmospheres and bacteria using sulfur as energy. I believe complex life could exist on planets slightly larger than Mars, similar to Earth, and even on super-Earths 2 or 3 times the size of our planet. However, billions of years is a long time, and as you know, life requires tranquility to evolve. A planetary shield that prevents a significant number of impacts is necessary. This shield could be a moon or several moons, or even gas giants in the system, which could be sufficient. Having a moon is not an indispensable requirement, but it greatly helps. Complex life is not as resilient to temperature changes, so the planet's temperature should not be too hot or too cold, ideally between -3 degrees Celsius and 45 degrees Celsius. Beyond these limits, the development of evolved life becomes challenging. I highly doubt that complex life could exist on satellites of gas giants for the simple reason that the massive size of the giant tends to attract too many bodies, leading to numerous impacts and resulting in frequent mass extinctions. Red dwarfs, being cooler than the sun, have their habitable zone closer to the star, which means their planet must be very close to the star. When a celestial body is close to another of significant mass, tidal locking occurs, meaning it always presents the same face to its star. This results in the planet rotating and orbiting the sun simultaneously. Consequently, a planet orbiting a red dwarf would experience eternal nights on one side and eternal days on the other. However, plants and animals could potentially develop in a narrow strip on the sunlit side where temperatures are more stable. Given that 90% of the stars in the universe are red dwarfs, I am convinced that the majority of simple and complex life forms in our galaxy exist on a planet orbiting a red dwarf. Summarizing, for complex life, we need F, G, K, and M-type stars of population 1, a habitable zone, a rocky planet, a protective atmosphere, stable temperature, liquid water, and a planetary shield. Astronomers could detect the presence of life through the emission of gases such as methane and oxygen, which would indicate the presence of life, including photosynthetic organisms. Living beings always contribute to changing the original atmosphere. For intelligent complex life, the requirements continue to increase. In my view, only F, G, and K-type stars would be good candidates for this type of life. We know that for intelligent beings to exist, there must first be microorganisms, followed by plants or other organisms that provide multiple levels in ecosystems and give rise to more complex life. In other words, intelligent life is impossible without other living beings. Now you understand that when a forest is burned or a species is extinct, humanity dies a little more. M-type red dwarfs are highly unstable and more active than our sun. While many of them may have planets with plants and animals, intelligent life is too fragile to develop on a planet with tidal locking, where photosynthesis would not exist on the dark side, and the environmental changes on the sunlit side would be so significant that they would destroy any possibility of evolution towards intelligent life. Adaptation to an aggressive and hostile environment is crucial, along with other conditions such as a planetary shield that balances the axis of rotation, a magnetic field that deflects harmful radiation, and stable temperatures. Therefore, for intelligent life, we need F, G, and K-type stars of population 1, a habitable zone, a rocky planet, liquid water, a protective atmosphere, stable temperature, as well as living beings such as plants and animals, and a planetary shield. Like other forms of life, the emission of certain gases would be indicative of a planet with life, although at the moment, there would be no way to distinguish between simple, complex, or intelligent life. Spacefaring technological life requires all of the above, with one important detail: it is very likely that intelligent life capable of space travel on super-Earths may not be possible due to the significant gravitational forces. Planets with 2 or 3 times the gravity of ours would make it extremely challenging to overcome gravity and venture into space. We struggle enough with Earth's gravity, so imagine planets with triple the gravity. I can envision millions of worlds with intelligent beings on high-gravity planets, tightly bound to their own planet, where space travel would be a utopia. On the contrary, planets with low gravity could give rise to civilizations of aviators. Astronomers could detect the presence of life through the received light or radio transmissions. The emission of greenhouse gases would indicate the existence of life in the midst of industrial development. In its early stages, intelligent life can be very noisy and detectable. However, if all civilizations in the cosmos go through this process in just a few hundred years, it's possible that we may not detect any of them. If they have technology far superior to ours, they could be undetectable by our instruments. However, we could potentially detect artificial lights or small fluctuations in the planet's brightness, which would indicate the presence of large structures. Currently, it's impossible to detect artificial lights on planets in other systems with our current technology. In the next generations of telescopes, there is hope that they may reveal some of these mysteries. In this brief analysis, we have seen that microbial life should be quite abundant, especially around red dwarfs, while life like ours is rare. Astronomers always determine if a planet has liquid water and is in the habitable zone by analyzing the light it receives, which provides valuable information. It's the first step. There could currently be life in other places that we cannot capture. We eagerly await the James Webb Telescope and the Extremely Large Telescope, which will hopefully analyze biomarkers in the atmospheres of thousands of already discovered exoplanets, many of which have enormous potential for life. If you enjoyed this video, please like and subscribe, activate the notification bell, share on social media, and leave your comments.